for our last couple of questions here, we're going to determine, now that we know what a polar and a nonpolar bond are, we're going to say, well, how would you know if a bond is going to be polar or nonpolar? This is going to be different than how you can tell if a whole compound is polar or nonpolar. We're going to learn about that as we go through our bonding lab together. But for right now, we're just looking at the individual bonds. So to determine bond polarity, you look up the electronegativity value of the two atoms that are being bonded together. So if I zoom in on my Lewis dot structure here, this bond, for example, right here between the C and the H, if we wanted to determine if that bond was polar or not, we'd have to look up the carbon and hydrogen electronegativity values and find the difference between those two. These two numbers I grabbed off of an electronegativity chart. There is one available for you guys up on Schoology if you do want to see where I got these numbers from. But we found the difference between these guys and got a difference of 0.4. Or let's say if we looked at the difference right here between this bond right here between carbon and carbon. Well, the difference between carbon and carbon's value is 0. So what that means, like we were talking about before, that a carbon-carbon bond, they pull, the left carbon and the right carbon pull on the electrons with equal strength. And so that is as nonpolar as it gets. They spend 50% around their time around one carbon, 50% of their time around the other. Now, technically, carbon does have a higher electronegativity than hydrogen does. So the electrons do spend more time around the carbon than the hydrogen. But we're going to say anything where you find a difference between 0 and 0.4, we'll call that a nonpolar bond. Again, that doesn't necessarily mean that your compound is nonpolar. You have to look at each bond individually to decide polar or nonpolar. To decide if it's going to be polar, we're going to say that the electronegativity difference is 0.5 and greater, and as long as you have no metals involved in the bond. Because if you did look up the electronegativity value of sodium and chlorine, let's say, their difference is going to be enormous because sodium's on one side of the periodic table, chlorine's on the other, and so they'd have very different values, therefore their difference in values would be large. But we said before, anytime you had metal with nonmetal, we'll call that ionic. So as long as your compound, your bond that you're looking at has no metals involved, so you're looking at just nonmetals or maybe a metalloid, and you find the difference between those two substances to be 0.5 and up, then we'll call that a polar bond. So if you look up chlorine's electronegativity value, you would find 3.0 minus carbon's of 2.5, a difference of 0.5. So that's why I have this bond here. The carbon-chlorine bond is highlighted in blue, where all the other ones are highlighted in purple. So when you will use electronegativity differences, that's when you're looking at individual bonds. We will soon see, how do I know if I would call this entire compound polar or not? We'll learn how to do that soon, okay? But this last bit, unfortunately, the AP exam does not give you an electronegativity chart. So how are you going to know if a bond is going to be polar or not? So I have this little mnemonic device. I'd like you to think of a couple words here: phone call and speech. So phone call, if you want to spell it out phonetically, FONCL, so fluorine, oxygen, nitrogen, and chlorine. And then I have this big dark bar, and then underneath, speech. Think of the word speech. S, sulfur, phosphorus, carbon, and hydrogen. So if you were looking at a bond between F and O, let's say, so we were going horizontally here between F and O, or between F and N, or between chlorine and oxygen, These guys all above the dark heavy line, their electronegativity values are similar enough that if you were to find the difference between their values, they would all fall in that 0 to 0.4 range. Similarly, down below, as long as you're going left to right, so sulfur to carbon, phosphorus to hydrogen, carbon to hydrogen, anything left, right, the electronegativity differences would be very small, so a nonpolar bond. However, if you cross that heavy line, if you bonded fluorine to hydrogen, let's say, or nitrogen to sulfur, for example, anytime you cross the line, that's when our electronegativity differences start to get larger and we have a polar bond overall. The fluorine, oxygen, nitrogen, chlorine, those are our elements that have higher electronegativity values, so they would be the electron hogs in those polar bonds.